Well, hello again everybody. Well, I'd like to start off today by thanking everybody who watched my last video and also bothered to take the time to leave a comment and some advice on what we should do with this battery eliminator. Now, one or two people said that it was probably beyond repair, and because it was beyond repair, probably the best thing to do was just to leave it as it is and just keep it as a bit of a curiosity. And to be honest, I actually think that is quite a reasonable response and not actually a bad idea. But the majority of people said that they would actually like to see us doing a restoration on this power supply. And I've got to admit, I'm kind of itching to do that myself. You know, I got quite excited when I saw this. I think the thing that I'm most doubtful about, though, is these transformers. Well, this one's a transformer. This one over here is just a smoothing inductor. But the wiring is in such bad condition. It's not just that the wiring is cracking. You can see the insulation is peeling off, it is breaking off. But actually the insulation is broken off the wiring as it goes into the transformer bobbin here as well. So you're actually looking at the top of the transformer now, and we've got two wires that come out of the top here. Now this is the secondary winding. One of the wires goes to the bank of smoothing capacitors and then onto the 0 volts output, and then the other wire, this one that I'm shaking now, this wire goes on to to one side of our metal rectifier. Now, one of the things that I think is interesting about this transformer is, hopefully you can see that we've got these what look like windings on it. And taking a close look at these, I think I said in the last episode that I couldn't see any varnish on them, but taking a closer look, I think the reason they're not varnished is because these aren't actually windings as such. I actually think that this is the core of the transformer, because if I take a magnet, let me get a magnet now, and just touch it to here, it actually sticks to this. So this is iron. So I actually think that these windings are the magnetic material. Now, I'm used to seeing normal style transformers that have E and I cores that are stacked together. Of course you do get toroids, which I think have like a magnetic former in the middle of them, but this one, yeah, I think that this winding here is made from soft iron, and I think that this winding, this outer winding, is actually the magnetic core of the transformer. And as another test, if I just take my meter here and I've got it set to continuity, I don't know if I'll be able to make a good connection on here, but we've got a metal screw here. So if I touch that and now I touch these windings, you can see that they're all part of the same circuit. There's no enamel on top of here. This metal here, it's I think it's a core, or it's some form of shield. I'm going to go for it's a core of the transformer, that's what I think it is. But going back to the wiring, one of the things that I'm a bit doubtful about whether or not we can repair it, you can see that the wires are actually going into the core here, but the insulation is broken off them as it goes right into the, let's call it the bobbin, and I'm not sure we'll actually be able to insulate these safely or not. So I think the first thing I'm going to do on today's video is I'm going to try to disconnect these windings without doing too much damage. And what we'll do is we're going to do some insulation resistance testing, maybe just verify if this transformer is still good, because, you know, any power supply, the transformer's the foundation. If we haven't got a good transformer, we've got nothing. Now, if we find that these transformers are no good and they're beyond salvage, we can't make them repairable safely, I think what we'll probably do is we'll just go ahead and we'll take this transformer out and we'll try to replace it with, I don't know, something a bit more modern from a scrap set, because at the end of the day it might be quite useful to still have a battery eliminator, especially one as early as this. So I'm dating this, I'm still going to say I think it's around 1929, because I've seen some articles that feature something very similar from around that date. Of course it could be a little bit later, I'm not exactly sure. So we mentioned earlier we've got these top windings here, so these are the secondaries, and then we've got the primary windings down here. And the way I think it works is we've got a couple of wires that are bunched up here. So this was the incoming mains supply. Can I just pull these through? Well, they've got knots tied in them, but what I think happens is, actually this is a more modern cable, because I can actually see that, oh maybe not, it's got brown conductors in it, but they look like plastic. So what we've got is we've got the live and neutral coming into the transformer. One of the wires goes straight into it, into the bottom here, into the bottom of the transformer. But we've got two other windings coming out from the transformer, and they go to this contact block here. And I think this is the neutral wire, and I think the idea is, depending on what voltage you want to select, it's got a stepped primary winding, so you can select from maybe, I don't know if it says on here. Fortunately, I can't quite make out the writing. So I'm going to cut that. That's beyond use. So I think that was probably our neutral wire, but it wouldn't make any difference if it was live or neutral. And then on the underside of here, we've got two of our primary windings, our tappings. Now I suppose I should actually try and put a label on these windings to try to show what they are. Give this a clean, maybe I can actually make out what it says then. It is a little bit difficult to make out the writing on here, but it looks like 200 to 20, and then on there I think it says 250 to 50. So yeah, it's some kind of tapping selection. I think what I'll do is I'm just going to put some labels on these windings, and then I can put them back in the right order. So I'm going to cut off the 220 winding first. Let's just snip that off. You can see pretty much all the insulation is broken off it. So there's 200-20. Let's disconnect the other winding. And that one's 250-50. And then this is a live wire coming into it here. So we're going to cut that off. And I think I will mark it live, although we know what it is, don't we? I'm going to call it live. It could equally well be neutral. Wouldn't actually make any difference to the operation of it. Now we know that these windings here are secondary, so we're going to give them a cut. And I think to make this transformer a little bit easier to manipulate and look at, I think we need to take it off the frame, take it out of its enclosure, so we can look at where these windings enter the bottom of it. So let's undo it. And let's see if I can undo it using this universal spanner. Could be at this a long time. It's a pretty long screw this. I could be at this a while. Wow, I've got cramp in my wrist. Oh, there we go. Ta-da! There we go, got it out. Actually, all the insulation has completely come off these wires, and I just don't see any way that we'll be able to insulate them. Now, certainly I think I might have been able to get at this winding here and maybe put some insulation as it enters the bobbin. But this other wire next to it, it does run under this steel material for quite some way, and it runs under it without any insulation. All the insulation has gone away, and you'd have to take the steel off it, the steel windings off, to actually expose the part of the transformer to get at. I'll tell you what, I'll keep prizing away. Maybe we'll be able to see it. I think the top windings are secondary. I think I could probably get at them to put some insulation on them. I think what I might do is, because I keep catching them, I think we're going to cut these back because there's more chance of breaking them off. So let's cut them back a bit. So I think then we could possibly just about get at them. But these, I don't know. So yeah, I think it might be possible to insulate that one. Will this winding pull out? Ah, okay. Is that getting us somewhere? I don't know if we stand any chance of actually getting these windings back again, but given that this transformer's broken as it is, we're not losing anything, are we? Okay, so hopefully you can see that. Can you see we've actually exposed where one of the windings enters into the inner bobbin, so that's exposed now, so we could graft a new piece of wire onto that one at least. Okay, hopefully you can see that. We can see where the wire disappears into the bobbin. We've actually just managed to bend out some of the soft iron core out of the way. Let's try and expose a bit more. It's almost like it's wrapped in a basket of steel, this bobbin. That's probably a good description of it. It's wrapped in a basket of steel. What we're trying to do is we're trying to take it out of its basket. Are we exposing where that goes in? I mean, we could do all this and we might still find it's gone inside. I've got to go further. It's not going to be much left by the time we've done. So I've gone ahead and I've prized away all this steel, and hopefully you can see now that we've actually exposed the point where these wires enter the bobbing. Now, I guess what we don't actually know is, for all we know, these wires could be shorted out inside, or yeah, we don't know what sort of condition they're in. All we can start to do is do some testing, isn't it? So I guess this is the point where maybe we get the megameter out. Now, as I mentioned earlier, I've never seen a transformer like this before, so I did actually post some pictures of it on the UK Vintage Radio Repair and Restoration Forum, and just asking for some any advice or help. I mean, one of the things that I asked for is, what do you call this thing? And a few people have said that, well, one of the common names that people used to call these things, they used to call them a hedgehog, and I guess we have revealed the spikes on the hedgehog here, so that does sound like a good name. The other people have described it as an inside-out toroid transformer, so yeah, that kind of makes good sense. So it's an inside-out toroid transformer, and apparently one of the reasons that they made it this way is because back in the day it would be quite difficult to wind a toroid, whereas this just has two bobbins of wire kind of stacked on top of each other. So I guess this was much easier to make and probably fairly cheap to make than maybe stamping out all those pesky E&I laminations, so maybe that's why they did it. Although then again, equally well, it could have been something that they charged extra for because it made the sound better. You know, who can tell why it was done like that? I don't know. But thanks for all the people in the forum who reached out and gave me some help. It's always appreciated. So I think we'll make a start by just testing the continuity of the primary windings, so let's just do that. So 54 ohms, so I suspect that that's one of the tappings we've got there. And then 350 ohms to the far end of the winding, so don't know what the value should be, but that doesn't seem too disastrous. That's probably about what I'd expect. And I would have thought that the secondary is probably not too dissimilar. Okay, so that's 380 ohms, so yeah, definitely in the ballpark. Let's just switch our meter leads round and then we will do some high voltage insulation resistance checks. So let's put one clip on the secondary there, and we'll put another clip on the primary and do our test. I think that's coming up clear. Let me just test our meter. Yeah, that's okay, so double check that again. So let's also go ahead and just check we haven't got a short circuit between our primary winding and these core windings. So that looks okay. And let's just do the same for our secondary windings. So that looks okay. Okay, so I don't know if it'll work as a transformer, but insulation resistance checks look good, and also it looks good for continuity on the windings, so we stand a chance. The other thing I'm not sure about is how neat a job we'll be able to make of folding these wires back, these iron wires back down. We'll have to have a go. So what I plan to do is I'm going to sleeve each of these as tightly as I can. And then what I think I'll do is I'm going to use some epoxy resin, and I think I will try to put a layer of epoxy down on top of here, and then I'm going to fold the windings back down on top of it. So that's my plan. Maybe I'll be able to get a few little layers of Kapton tape again just between these windings, but I'm going to glue everything down with epoxy so that nothing can start to vibrate and start to rub away at the insulation. So that's my plan. So I'm just going to try and insulate these wires here and stop them moving around with some epoxy. And I've actually got some of this 90-second epoxy, which I didn't necessarily want it. It's just what was available. And 90 seconds, that really doesn't give you an awful lot of time to get it wrong, does it? We'll have to see how we get on with it. My hope is that this is going to not just bond the wires down, but it is also going to work and provide a little bit of insulation just in case anything goes wrong. And I've not got a lot of time to think about this. There's blob number 2 and our last blob, and I can feel it. Yeah, this stuff is setting already. It really does go off quickly. So that's the primary. What we'll do is we'll give that another 10 minutes just to go off and set a bit firmer, then we'll turn it over and we'll do the secondary side. Hopefully that might be a bit easier. Well, as you can see, I've gone ahead off camera. I've finished our transformer. I've put some longer wires on it to extend the original ones with the insulation that would have broken off on it. And I've also, where these original wires go into the transformer, I've covered them in heat sleeving, and then I've actually just put some epoxy in just to retain them and to stop any vibration from these core windings around it, just in case the vibration might have been rubbing against the very thin heat shrink. It might have cut into it and caused a short circuit. So I've done that. I've also given it a wrap of gaffer tape because the original ones just seem to have some gaffer tape around them, so I think that doesn't look too bad. And I've also gone ahead and put the insulation resistance tester over it, and it survived. So yeah, I'm hopeful that when we put some power on this transformer, it will actually work like a transformer. But yeah, don't want to count my chickens before they've hatched, so we'll put that on one side for now. So having gone ahead and completed the little repairs to the mains transformer here, I went and removed the inductor from our power supply, and that's really had the same treatment, and I didn't show you that on camera because it was exactly the same simple process. Well, as you can see, I've actually got some information about our Regentone battery eliminator, and this is from the Wireless magazine of July 1929. So I'd like to thank Steve, who actually sent me a link to this information, and again I will put a link to these magazines in the show notes, so if you want to download these old radio magazines and have a look at them, you can actually get access to them. But the advert here, it's got the same unit, so it says model W.I.B, which is what we've got. So again, I can only assume that the B must mean for B plus for the high voltage battery, and it says for AC mains, and apparently this cost £4.19. I'm going to have to do that little cost accumulator, because I'm guessing £4.19 must have been an enormous amount of money in 1929 for this battery eliminator. Now, unfortunately, it doesn't actually have very much information. It's really just an advertisement. It says there's no more satisfactory source of power for your set than a mains unit. There is no mains unit on the market more satisfactory than the Regentone. Well, maybe that remains to be seen. We don't actually know that. So it says for AC models incorporating the Westinghouse metal rectifier. So again, that just confirms that the rectifier we looked at earlier was a Westinghouse unit. So I've also got another article from a magazine, which is actually a year later, February the 19th, 1930, and this is a list of manufacturers of various battery eliminators. So I can see there's Haddon's and Poppard, I think it is, Fermion, Power Equipment, Radley, Radio Volt, Reeds and Morris, and here's ours, Regent Radio Supply Company. And it's got the unit here. Well, it's not actually got the exact unit. It's got what they call the W.I.B SG. Now the SG stands for screen grid, I believe, so I think this was a slightly different unit to the one I've got. So W1B SG, it says it's HT, and it had a 20 milliamp at 130 volt output. Now in the same magazine, a couple of pages on, there is also a little symposium about actually dissecting the battery eliminator, and it gives you some ideas on how to build your own. Now there was very little information really about the specification of our WB one, so we know that probably the transformer might output 19 milliamps, but this article here says that the smoothing choke should be, well, typically it says it should be having an inductance of some 30 henries or more. So it just so happens that we've got our smoothing choke here still on the desk, so we could actually just measure to see if this is in the ballpark of 30 henries. So you can see on the bench I've actually got my dairy meter, and I've actually had to get this out because when I tried to measure the inductance with the peak, it basically just didn't want to know. So I'll show you that in a minute. Now it could be that the actual amount of henries, maybe it exceeds what the LCR meter can measure. I'm not sure what the specification is for the inductance measurement on the peak, but yeah, it didn't want to measure it anyway. So let's try the dairy meter, hopefully that'll give us a reading. Okay, so it's actually telling us that our inductor, it's actually 25.97 henries. So yeah, so we're actually about 4 henries short of the 30 that the magazine article gave us. So yeah, basically they were a bit stingy, weren't they, on the copper. According to the magazine article, they should have actually put a few more turns on this inductor and give us our 30 henries, but they've just given us 26 here. Maybe that it's not quite true that no expense was spared, because they did spare a little bit when they wound this inductor. Now strangely enough, if I actually take the peak LCR meter, I do actually get a different reading, or in fact no reading at all for inductance. It actually thinks that this is a resistor of about 1 kilo ohm. So I'm not exactly sure why the peak LCR 45 doesn't measure that. Maybe it's outside its inductance range. I'm not exactly sure. I don't know what the specification is, but certainly yeah, it doesn't want to read the inductance. Off camera I've already done an insulation resistance test on our transformer here, but I know you guys feel a little bit short-changed if you miss anything, so we're going to do that again. So again, typical transformer tests that you do on any transformer, you want to do an insulation resistance test between the primary and the secondary windings. In fact, I've got that the wrong way around. The primary windings are at the bottom here with this multi-tapped primary winding, and then we've got the 2 wires here that are the secondary. So you want to look for insulation resistance between the primary and secondary, and you're looking for a higher value as possible. Now typically you do test at twice the rated voltage, so on this meter that'll be 500 volts. So what I'm going to do is I'm just going to short the 2 secondary wires together, and then ideally we would do the same with the primaries, and then turn the meter on and hope for a high reading. Okay, well this meter's actually reading infinity, so yeah, it's clear we've got no resistance between the primary and the secondary. So I always like to confirm that the equipment's actually reading right, so let's just bring the leads together. Yeah, okay, so we know the meter's good. Turn the meter off so I don't get an electric shock. So that was an insulation resistance between the primary and secondary. Now the other test that you want to do is you want to make sure that there's no short circuit between any of the windings and the core of the transformer. So the way that we do that is we actually get all the wires, and I'm going to short them all together. Hopefully that's got it. And now I'm going to put the clip onto the metal of the transformer, the metal part. Let's turn on again. And again, we've got a high reading, in fact reads infinite on this meter. Again, just always check the meter. Yeah, the meter's reading good. Okay, so from an electrical safety point of view, certainly there isn't any short circuits between the primary and the secondary, or any of the windings on the to the core. So in theory, you know, we could apply power to this and then touch the transformer and we shouldn't get an electric shock off it. Well, as you can see, I've gone ahead and I've got out the variac and the lamp limiter, and I've got a watt meter here which is also going to read off our voltage. got our transformer tucked away in the background, and we've got a voltmeter which is connected to our secondary. So I think the first test that I'm going to do is, let's just put some power onto it, and I've actually got the transformer set to, well, I've got the full winding, the full primary winding connected, which is connected between the live and the, I don't know, 230, 250 volt tapping. So what we're going to do is we're going to wind up the voltage to 250 volts, and then we're going to see what the secondary voltage is. Now we've got no load on the transformer, but what we'll do is we'll wind the voltage up to 250, we'll see what the secondary voltage is, we'll divide the primary voltage by the secondary voltage, and that's going to give us the turns ratio, which is it's a nice little characteristic of a transformer. It's nice to know. So yeah, that's what we're going to do, and I guess we'll turn the power up relatively slowly, because this transformer's probably been asleep for the best part of, well, I suspect probably more than 80 years, could be even longer. So let's wake it up a little bit gradually. We've got the lamp limiter on, so if anything goes catastrophically wrong, the lamp should come on. So switch power on, turn the variac down. See if I can get it dead on 250. Okay, 250.1. So we've got 250.3 volts going into our transformer now, and looking at the secondary voltage, we've got 182 volts coming out of it, and the transformer's off load. We've got no resistance, we've got no load connected to the secondary. With that information, with those two voltages, I can divide by one by the other to give us the turns ratio. So all I've got to do is I've got to take 250, I've got to divide that by 182, and that equals 1.3. So the turns ratio of this transformer, it's 1.3 to 1. So for every one turn on the secondary, there's 1.3 turns on the primary. After finishing our last test, I've actually left the transformer just sat there powered up, and it's been powered up for probably about an hour. And if I just grab hold of it, I can actually feel that it's warm to the touch. It's not hot, but it's definitely warm to the touch, so it's actually heating up. Well, the fact that it's heating up, I think, is quite interesting. Now remember that we haven't actually got anything connected to the secondary of the transformer apart from this voltmeter here, which really isn't putting any load on the transformer at all. So what that tells us is that, well, we're actually putting energy into the transformer and we're not getting any useful work out of it because there's no load connected. So this heat that we can feel at the moment, this is all wasted energy, it's inefficiency. So if you just swing in and take a look at our energy monitoring plug, we can actually see that it's actually showing 3 watts at the moment. So 3 watts of power, they're actually going into this transformer and they're not doing any useful work. Actually, all they're actually doing is they're heating up the transformer and they're going straight up the chimney. So we've got 3 watts of power there, which is just heating the world. Now when it comes to transformers, there's actually several different mechanisms which can result in loss. Now the easiest of transformer losses to explain is the copper losses. So as we all know, transformers have a primary winding and the secondary winding, and in effect all those windings is very long lengths of wire that have been wound into a coil. Now we all know that lengths of wire have resistance. The longer the length of wire and the smaller the diameter of wire, the more the resistance will be. When we have the transformer loaded, we have currents flowing in both the primary and the secondary windings. And because those currents are effectively flowing through a wire that has resistance, as we all know, when current flows through a resistor, the resistor will get hot. Now there's actually several different ways that we can actually measure or calculate copper losses, and we'll try that later. The second group of losses that can occur in a transformer are called core losses. Although core losses are very commonly referred to as iron losses, so iron losses and core losses are actually the same thing. Sometimes I think it's easier to think of a transformer like a machine, and like a machine it has different components. So you have a primary winding, and the purpose of the primary winding is to induce a magnetic field. It creates a flux in the core of the transformer. Now that magnetic flux travels around the core of the transformer until it meets the coil of wire which forms the secondary. and that magnetic flux is converted back from magnetic energy into electrical energy. So it is the magnetic properties of the transformer's core material which result in these losses, and they could be due to the type of magnetic material that's used or the construction of the transformer. And our core losses can be further subdivided into two different categories, and they're called hysteresis loss and eddy current loss. So let's take our eddy current losses first. Now we already know that the magnetic flux circulating in the transformer will induce a voltage across the secondary of the transformer. But in most power transformers, the core material itself is also made out of a material that's conducting. So you won't just get an EMF induced in the secondary of the transformer, you will also get an EMF induced in the core of the transformer as well. And that EMF goes on to induce currents to flow within the magnetic material itself. Now those currents aren't actually doing anything useful. All they'll be doing is acting on the resistive core material and actually giving rise to heat. And so the eddy current loss is another mechanism which actually makes our transformer get hot to the touch. And conventional transformers have a laminated core. And the reason that they have a laminated core is to make the electrical resistance of that core very high. So that's to reduce the circulating currents and reduce the eddy current losses. The final type of transformer loss that I'm going to talk about today is hysteresis loss, and this is another of our iron losses. So at this point in the proceedings is where I would normally present a hysteresis graph, and I believe the purpose of this hysteresis graph is to show that the magnetic material in the transformer needs slightly more energy to reverse its direction of magnetisation. But I have to say personally I've never really understood this graph very well. In normal operation, our transformer is going to be fed from an AC supply, and so the current in the transformer is going to be going in a forward direction and then a reversing direction 50 times a second, because that's the frequency of the mains in the UK. Now, because our current is alternating, the magnetic flux which we are raising within the transformer will also be going forward and in a reverse direction 50 times a second. Now I'd like you to imagine that you're part of the core material of the transformer, so let's imagine that you're a molecule. And when the current is flowing in a positive direction, you're going to align yourself with the north pole of the magnetic field. Now when the magnetic field reverses, you're going to turn around and you're going to face in the south direction. And you're going to turn round 50 times a second as the magnetic field reverses. Now of course you're not the only molecule in the core of the transformer, you're actually stood next to all your friends, and all your friends are going forwards and backwards at 50 times a second as well. Now imagine you're in a room full of people and they're all constantly turning backwards and forwards, facing in one direction and then another. Well, of course you're going to end up rubbing against each other, and we know that when things rub against each other they get hot. So that's what's going to happen as our molecules realign themselves in the north and south direction. They're going to rub against each other, and that rubbing against each other, that friction is going to give rise to heat, and that's effectively another of the losses in our transformer. So we're going to notice the hysteresis loss because our transformer is going to get hot. So in conclusion, we've looked at three types of transformer losses today. The first type of loss was copper losses, and copper losses are due to currents flowing in the primary and secondary windings. And because those currents are flowing through a wire that has some resistance, the windings will tend to heat up. And that heating isn't doing anything useful for us, it's just a loss. The second type of losses that I mentioned were eddy current losses and hysteresis loss. Eddy current losses being due to currents which are circulating within the core material, which give rise again to heating. And finally, hysteresis loss, which is due to the effect of the friction between the molecules as they turn forwards and backwards in response to the varying magnetic field. So having thoroughly mangled up probably a large number of scientific principles there, I think it's time to actually get back to the workbench and let's see if we can just measure the overall efficiency of our transformer, and then maybe just see if we can split it into the iron losses and the copper losses. Now I'm afraid previously when I measured the iron loss of our transformer I maybe got a little bit ahead of myself, so I've decided just to take a step back. Now one of the reasons that I did take a step back is because I found out that this energy monitoring plug that I was using here, it isn't actually very good at measuring wattage at a low value, at anything below about 10 watts. it seems to be very inaccurate. So what I've done is, you can see I've got another piece of test equipment on the bench because I do want to repeat those experiments. But the piece of test equipment that I've got on the bench is actually just a much more accurate watt meter. So this one is a feedback electronic watt meter, and for those playing along at home, the model number is the EW604. So just to explain the test setup at the moment, so we've got the variac here, and the variac is being used to provide the power to the input of that transformer, and the transformer, it's actually on the 220 volt tapping at the moment, and that tapping is from 200 to 220 volts. So what I've done is, with the supply from the variac, I've kind of split the difference, so I'm providing the transformer with 210 volts. So the power's coming from the variac, it's going through here, which is measuring the voltage because it's more accurate than the meter on the variac, and then that power is going into the watt meter here. So it goes into one side of the watt meter and it comes out at the other side, and it goes into the primary of the transformer. So again, all our watt meter is doing, it's measuring the total power which is being supplied to this transformer. Now the way that true power meters operate is actually quite interesting. So to calculate power, you have to know the volts and you have to know the current. And normally you would just do volts times amps equals power. But the problem with AC circuits, and when you're delivering power to an inductive load, which what a transformer is, unfortunately that voltage and that current, they're not in phase with each other, so you can't directly multiply them together. Now if you were to do the calculation manually and measure the voltage and the current using separate meters, you'd also have to measure the phase angle between the voltage and the current, and the phase angle is how much the voltage and current are out of phase with each other. So if you know the phase angle, you know the voltage and you know the current, you can then actually calculate what the true power is. But this meter does all that clever stuff, it does all that clever maths internally, and just actually displays a meter reading here which is showing true power. And taking a look at our watt meter reading here, I can actually see that it's about 7.4 watts. So we're delivering 7.4 watts of power to our transformer. The needle is just bouncing around very slightly, and the reason it's bouncing around is because the supply voltage to my whole house is just varying a little bit. It's going up and down, so that means that the amount of power being delivered to the transformer varies as well. But it is pretty much 7.4 watts at the moment. Now I've also gone ahead and I've actually connected a resistive load to the secondary of our transformer. So the transformer is now actually delivering some useful power, and it's delivering that power into a bank of resistors here. And I purposefully arranged this bank of resistors to actually present a 20 milliamp load to our transformer, because according to the specification sheet that came with this W.I.B, it does say that the output current was 20 milliamps. So we arranged those resistors so that we were drawing 20 milliamps of secondary current. So we can see that on this meter here. Well, it's just over at the moment, 20.1. Now I've also got a voltmeter on the bench, so what this is doing, the voltmeter is measuring the voltage across the load resistors here, which is actually the secondary voltage of the transformer, and that's 160 volts at the moment. Now because our load is purely resistive, it doesn't have any of that naughty inductance nonsense. All we actually need to do to work out the power which is being delivered by the transformer into our load here, we just have to multiply the voltage, which is 160, we have to multiply that by 20 milliamps. So I'm going to go ahead and do that now. So we'll take our calculator, we'll type in 160 volts, we're going to multiply that by 0.02 for 20 milliamps, and that equals 3.2. So that's 3.2 watts being dissipated in our load. So remember previously we were actually supplying 7.4 watts of energy to our transformer, but we're only getting 3.2 watts of useful energy out of it. So I'll just take our figure of 7.4 and I'm going to take away the 3.2 watts of useful energy, and that leaves us with 4.2. So this transformer, in actually delivering its 3.2 watts of energy, it's actually consuming 4.2 watts of energy. So it's really not very efficient. It's actually using more energy than it's giving to our load. So this is quite an inefficient transformer. Now the other way to express efficiency is as percentage efficiency, so we can also do that. And the calculation for efficiency is the output power, which we know is 3.2. We need to divide that by the input power, which we know is 7.4. equals 0.43, but we have to times that by 100, multiply that by 100, and that equals 43%. So our transformer here is actually only 43% efficient. Now, as the wife said to me the other day, size does matter, and it's especially true when it comes to transformers. And as it turns out, the efficiency of a transformer actually increases with scale. So small transformers like this are usually relatively inefficient, but we would probably still expect a modern transformer, even a small one, to achieve better than 60% efficiency. A large transformer could be between 90 and 94% efficient, but yeah, a small transformer like this may be 60% efficient, but we're actually considerably below that. We're only at 44% efficiency, and you know, I'm not actually surprised because this transformer is actually getting quite warm to the touch. So we've got 4.2 watts of losses at the moment, but we don't know how much of that 4.2 is due to iron losses and how much of that 4.2 watts is due to copper losses. The actual iron and copper losses will be adding together to make the total value of 4.2. But what we can do is we can rearrange this test setup to try and measure the iron losses and the copper losses. So I'm going to have a go at doing that next. So I'm going to repeat our core loss test again, and I'm going to use the feedback meter to measure the power as opposed to this wall wart power meter, which is inaccurate. So this particular test that we're conducting is known as the open circuit test, and the reason it's called that is because the actual output terminals of the transformer, the open circuit, we've got nothing connected to them. So at the moment the transformer is actually not delivering any useful power, but if we actually look at the indication on the power meter, it's actually consuming 4 watts of power. So the transformer's consuming 4 watts of power but outputting none. So the actual total core loss is actually the 4 watts. Now a few moments ago we measured the overall loss within the transformer system, and we actually only measured 4.2 watts of loss, and that would have been iron and copper losses combined. So the fact we've just measured our iron losses as 4 watts, that would probably predict that our copper losses should be around 0.2 if they're to add up together, which in theory they should do. So let's go ahead and let's now conduct the slightly more interesting short circuit test. For our next test we actually have to short out the secondary windings of our transformer, and I'm actually going to short them out using this fluke meter set to its amp range. And the reason I want to do that is because we need to know when the secondary winding is passing its rated current. So let's just take the secondary windings and put them into these crop clips here. Now obviously we've got to be quite careful when we do this test. We've got to use the variac to wind up the voltage until we achieve 20 milliamps on here, and yeah, we've got to be very careful, because if we're not careful we could burn out the transformer if we put too much voltage on the primary. So after first checking that our variac transformer has been turned fully down, we can switch on. And we're now going to very carefully turn up the variac until the secondary current measures 20 milliamps. Now remember, we're using 20 milliamps because that's what the transformer specification said that the rated output was. Now I'm actually only turning this up. I suspect we've only got a few volts across the primary of the transformer. It doesn't take a lot of voltage to induce a secondary current of 20 milliamps, so I'm really being careful. So if we take a look at our power meter, we can actually see it's indicating about 0.3 of a watt. Now I estimated that the copper loss should be about 0.2 of a watt, so we're actually measuring slightly more than that. So there is some measurement errors creeping in, but I don't think we're far off. So it does look like the majority of the losses of this transformer, they're actually to do with the iron core of the transformer. They're all iron losses. The actual copper losses are really quite minimal. Well, I guess considering how the magnetic material is just wound effectively around the outside of the transformer, I'm guessing it's not really that surprising that in terms of iron losses it's not particularly good, this transformer. So it's probably to do with the way that this transformer is relatively inefficient, relatively poorly manufactured. And I'm also guessing that probably in the last 80 years the actual steels that this transformer is made out of, they've probably developed much better magnetic materials, because after all this transformer was built around 1929, so it really isn't doing too bad for its age, is it? Well, I'm sure you'll agree when it comes to transformer efficiency, I think we've done it to death now, haven't we? So let's move on. So the next test that we're going to do is to investigate the voltage regulation of the transformer. So voltage regulation is a measure of how well a transformer will maintain a constant voltage over a range of load currents, and I think it's probably one of the most important transformer parameters. Now, for most transformer applications, when you load up the transformer and draw current from it, you wouldn't actually want the secondary voltage to drop, because the piece of equipment that you're actually powering up with the transformer, if the voltage dropped, it may not work properly. Now, in most cases with modern equipment, we've probably got a voltage regulator, but you can still come a dinkum, because if you actually have very poor regulation, you could maybe pull the output voltage of the secondary below the voltage at which the regulator will work. Now, you can also have the opposite effect in that if for some reason you stop loading the transformer and the voltage rises, you wouldn't want it to rise to a point where it might damage your piece of equipment. Now, the test for voltage regulation is very easy to do, and it's actually quite an interesting one to carry out. All that we have to do to carry out a regulation test is we just have to measure the secondary voltage of the transformer unloaded, so we've got no load on the transformer, and we can see it's outputting 170 volts at the moment. And then what we do next is we're going to put a load across the transformer, but what we have to do is we have to draw the transformer's rated current, and we believe that the rated current for this transformer is around 20 milliamps. But when you're doing the loaded test and the unloaded test, it's very important that we keep the primary voltage the same. So I'm going to try and just adjust the variac here to try to keep that set as close to 210 volts as possible. Just tweaking up the voltage very slightly. I'm afraid that my mains is going up and down, but we'll get it close enough. So we've got about 210 volts on the primary. We just need to make a note of this now. So we've got 171 volts on the secondary. So write that down, 171 volts. And what I'm going to do next is I'm going to install our load, but I'm actually going to connect our load via a milliamp meter so we can see what that load is. So I'm going to put the ammeter there. Now, I know I've actually got the watt meter on the bench at the moment, but that actually isn't used for this test, it just happens to still be here. So let's switch on, and I'm going to wind up the voltage until we've got 210 volts on the primary. Okay, so we've got 210 volts on the primary. We can see our ammeter here is drawing a 20 milliamp load from the transformer, and we can see that our loaded secondary voltage is now 159 volts. So you need to write that down, 159 volts. Calculators at the ready, everybody. So we found that when the transformer secondary was unloaded, we had 171 volts across it, and then when we loaded it with a 20 milliamp load, which is a rated load for this transformer, that voltage dropped to 159. So we've got a delta there of 12 volts. So as we loaded the transformer, the terminal voltage dropped, and that's quite normal for a resistive load. So to work out the percentage voltage regulation of our transformer, we've got to take these numbers and stuff them into a formula here. So what we need to do is we need to get the no load voltage, which is 171, take that away from the full load voltage, 159, and then we divide that figure by the full load voltage, which is 159 again, and then we multiply that by 100, and we should get our percentage regulation figure. So let's go ahead and do that. So we're going to do 171 minus 159, which is 12, and then we need to divide that by 159, and then multiply by 100. So we're going to have 7%. 7.54%, write that down. 7.54% regulation. Now, if such a thing existed as a perfect transformer, the actual regulation figure that we would be aiming for would actually be 0%. But actually, a transformer that has 0% regulation, that doesn't exist. So a transformer that had 0% regulation, what that would actually mean is that you could actually put as much load on it as you wanted, and the terminal voltage at the secondary wouldn't actually drop. Now for a modern low voltage transformer, regulation figures are typically between 4 and 6%, but for very high voltage transformers above perhaps 33 kilovolts, that figure can actually increase quite a lot, where it might be as high as 13%. So given the age of our transformer and given how crudely it's constructed, I don't actually think our figure of 7.5% is actually too bad. So based on our little experiment here, it would be quite logical to assume that as we load up a transformer, the output voltage will fall. Now unfortunately that isn't always the case. Depending on the power factor, you may actually find that a fully loaded transformer has a higher output voltage than an unloaded one. So I'll show you a little graph of that and leave you to ponder it. Well, I'm sure you'll agree we did end up taking quite a deep dive into the operation and testing of this transformer, and we actually went a lot further than we need to for a basic restoration. But the reason that I did that is for two reasons. One, I was just quite intrigued to see maybe how this transformer compares to a more modern one, and it would have been nice to have compared this transformer to a modern one to see the difference in the regulation and efficiency, but as it happens I don't really have anything suitable for hand at the moment, so maybe we'll come back and have a look at that on another day. But certainly I don't think that this transformer maybe lives up to the claims of its manufacturers about being the best money can buy. We certainly saw that the efficiency of this thing was very poor. It kind of uses as much power just sat there on the bench disconnected, with the output disconnected, as it does when it's fully loaded. So it's certainly not a very efficient, and also the voltage regulation is really fairly poor. But I suspect that probably doesn't make a lot of difference regarding the actual operation of this transformer in the battery eliminator. I'm sure it does actually do the job that it needs to do. And having thoroughly tested this transformer, we at least now know that it's going to work, because it was by no means certain at the start of this video. So we've got some other things we're going to look at next week, and I think what we'll do, hopefully we'll get this wrapped up next time. It'd be interesting to have a look at this metal rectifier, because I think the design of this again is quite interesting, so we'll maybe do a little bit of testing on this to see how it performs. And of course we need to have a close look at these capacitors, because I'm sure they won't be good, but it'll be interesting just to see what capacitance they've got and how leaky they've got. But again, we're going to have to depot these and put some new capacitors in here. So again, we'll do that next time. And then the final part of the puzzle that we've got to have a look at is this output potentiometer, which you can adjust the output voltage. Because when I tested it in video part 1, it did seem to measure open circuit. Now I can actually look at this, it appears to be bolted together. So I think what we'll have to try to do is we'll totally disassemble this, see if we can actually take it apart and find out what's gone wrong with it. So I think that might be quite an interesting thing to do. But I think for today, I think we've done enough, haven't we? So it's a nice place to finish of it today. So as always, thanks very much for watching. I hope to see you very soon, and I suppose it is that time of year, so wishing you all a very happy Christmas. Until next time, bye bye for now.